Okay, Michael, we can start now.
Okay. Thank you very much, Arvin. I apologize again for finishing early the last talk. I got confused with the timing. You owe you all 20 minutes, so whenever you want me to add 20 minutes to one of the talks we still have this week, let me know in advance, except for Friday when I'm busy. Okay, so now I'm trying to write on the board. Please tell me if it's not visible, too small, too large, or if I'm off the screen where you can see things, just let me know, okay?
Okay.
Okay. Thank you all. Okay, so we are interested in contraction theory. I want to explain what this is, what is a contractive system, how do we prove that the system is contractive, and then when we are done, apply all this to the ribosome flow model. But it is important to me to give you a general introduction to contraction theory because this is a really useful tool and it has been applied successfully not only for the RFM, but for many other models in systems biology. What I mean by this notation is that I have n state variables. Each one has its own derivative. It depends on time and on all the other state variables. And instead of writing these equations again and again and again, I just write them in vector form once and for all. So here we have n state variables. And here we have a vector f with n components, giving us the derivative for each of the components. Note the solution. I will send you, by the way, the lecture notes. This is the solution at time t when we started at times t0 at some initial condition A. So this is the notation of the solution at time t when the initial condition was A time t0. Is this still visible, what I'm writing on the board?
Yes, it's visible.
Okay, good. Very good. And now we say that the system is contractive if the following properties hold. There is some vector norm, and there is a eta which is positive, so that the solution emanating from the solution at time t emanating from A at time t0 minus the solution time t emanating from B at time t0 decays exponentially with time with respect to the difference between the initial conditions. So graphically, what this means is that if I look at two solutions, they approach each other at an exponential rate. This is what it means. And this is a very strong property. So we will speak about several things. The first thing is how to prove that the system is indeed contractive. And of course, the challenge here is that I don't know these explicitly. In a nonlinear system, of course, I don't know the solutions. I don't have a closed form expression for the solutions. And then the question is how to deduce that something like this holds without knowing the explicit solutions. And the second topic we will cover is, of course, after we prove that the system is contractive, how can we, what does this imply? Let let me just give you a simple example where we do know the explicit solution and we can prove contraction directly. And this is, of course, the example of a linear system. We have, and let's make life easy and even assume that it is a scalar linear system. So x and u are scalars here, and we look at the simplest possible linear system. X dot equals ax plus bu, and we assume that a is negative. Well, actually, we don't have to assume it now. We will assume it later on. And this is time varying because the control depends on time. Now, in this case, we know how to write. Let's assume that the initial time is 0, just for simplicity. And then we know how to write the explicit solution for the dynamics because we assume a linear system. So I assume that the initial time is 0 for simplicity. And then this is the solution at time t when we started at time t0 in the initial condition x0. And we have a closed form expression for this. And if I start, okay, let's call it a. Now a we already used, so okay, let's call it x0. Okay, now the initial condition is x0. And now if we start from another initial condition x1, then of course, this will be the same. This term, which is the effect of the control, we are assuming the same control. This will be exactly the same, and the only difference is that now, with this term that depends on the initial condition, it looks a little different. And now, if we look at the difference between these two scalars, then this is just this, because the term with the control is identical in these two solutions, so it just disappears. And then we see immediately that if A is negative, then we have contraction, because this is a decaying exponential when A is negative. By the way, this is meaningful also when A is positive, because it tells us something on the rate at which trajectories can pull apart. They can never pull apart faster than this exponent, even when A is positive. And when A is negative, we exactly have this structure of the distance between solutions decays exponentially to 0 with respect to the difference between the initial conditions. So contractive nonlinear systems are a generalization of stable linear systems. But of course, proving contraction in such systems is more complicated. Questions so far? I know that when I'm writing on the board, perhaps it's a little less clear or a little more clear than when I use slides. I don't know. So it's really, if you have any questions, please don't hesitate. Okay. Sorry?
No question at this point.
Okay. Okay. So, proving contraction in a nonlinear system is based on vector norms that induce matrix norm, that induce something called a matrix measure. This is what we need. These are the analytical tools that we need to prove contraction. So what is a vector norm? A vector norm is something that takes a vector and gives us the distance of this vector from the origin in some sense. So this will always be positive except for the 0 vector where it will be 0. This is my notation for a vector norm, so the norm of x. except when x is 0 and then it is 0. This satisfies the triangle inequality, and it also satisfies this equality for any real number C. When you multiply a vector by a real number, the norm is increased this way. So this is a vector norm. We are all familiar with this. Now, a vector norm induces a matrix norm. Then a matrix norm, denoted by 2 bars, is defined as follows. We have our vector norm. We consider the unit circle in our vector norm. So we go over all the vectors x that have vector norm 1 in our vector norm, whatever it is. Then we multiply a by x, we get a vector. And for this vector, we compute again our vector norm. So intuitively speaking, this is the maximal magnification we can get when we multiply a vector x by a. This is the maximal magnification in the vector norm that we can get using the matrix A when we multiply x by change it to ax. And an important property that follows immediately from this definition is this inequality that tells us that the norm of ax, the vector norm of ax, is always smaller or equal to the norm of x multiplied by the matrix measure, by the matrix norm of A. So note that this is induced by this, of course, because here I use my vector norm. Whatever vector norm I choose, I use it here, and of course I will get a different induced matrix norm. And eventually, we need to speak about the matrix measure, which is perhaps less known. I guess these two are usually known, mathematicians and physicists. The matrix measure is defined as follows. Is the limit as epsilon goes to 0. Let me write it here, please. It is defined as the limit as epsilon goes down to 0 of in plus epsilon a norm minus 1 divided by epsilon. So I will explain where this came from and make it more intuitive in a minute. But just let me explain what happens here. You take so A is n by n. Everything is n-dimensional. A is n by n. I take the n by n identity matrix. I add epsilon a. I get a matrix which is n by n. Then I calculate this matrix norm. I subtract 1, I divide by epsilon and take this to 0. This will be a number. And this number can be positive or negative. This was always in R plus. This is also always in R plus. But this can be negative, and this is important. Now I want to explain where did this matrix measure came from and what is it useful for. So to explain the matrix measure, let's consider a linear time-varying dynamical system. So x dot equals ax, but now a can change with time. And what I'm interested in is I fix some vector norm, and I'm interested in understanding how this vector norm changes in time. Because remember, what was contraction? Contraction was about how the vector norm of some vector, the difference between two solutions, decays with time. So in order to understand how the norm of some vector decays in time, we have to calculate this. Of course, this is not there is a problem here of it is not always differentiable, but let's ignore for the moment these technical details. And of course, if I want to calculate this, I need to look at this minus this, then divide by epsilon and take epsilon to 0. So let's look at this difference. What can I say about this difference? To first order in epsilon, this is xt plus epsilon at xt minus xt. And this gives me I plus epsilon a multiplied by xt minus xt, right? And now I use this nice property that said that the norm of this is always smaller or equal to this. I have this bound, norms that bounds the vector norm of the product of the matrix and the vector. So I can bound this by in plus epsilon a and you see that I just got this term that appeared in the matrix measure. So now I understand where it came from. Now, if I divide this by epsilon and take epsilon to 0, I get exactly this derivative. And here, I get exactly the matrix measure. This is exactly the matrix measure multiplied by xt. So the conclusion is, again, a little bit informally, that d to dt xt is smaller or equal to uat. I should have written at everywhere. A depended on time. Sorry. A was a function of time, but that's xt. And this is a scalar equation. Note that this is a scalar equation. Why? Because after I take the norm, this is just a number. And from this equation, I can conclude a very important formula, which is called Koppel's inequality. Koppel's inequality says, so let me erase this. I hope it's clear now where this matrix measure came from. Koppel's inequality says that xt is smaller or equal to E0t mu as ds x t0. Again, we are studying this system. We are studying the trajectories of this system. Koppel's inequality gives me a bound in terms of the matrix measure of A, and this follows immediately on this scalar linear equation. And this I try to explain to you just by looking at xt plus epsilon minus xt, the norm of x2 plus epsilon minus the norm of xt. Now, if UAS is all the time negative, then we get this is a kind of contraction result. Okay? This tells me that the solution of the system contracts at least at the rate eta with time. Questions up to this point? I'm sure that at some point perhaps I explained too quickly or without enough detail, or any questions?
No question.
Okay. Okay, can you see the board and can you hear me?
Yes, we can see the board. No problem.
Okay, okay. So I erase all this. I will just leave on the board I will just leave on the board this issue. We had a vector norm. This induced a matrix measure. And this induced, no, this is a matrix norm, I'm sorry. And this induced a matrix measure and we saw that at least for a linear system, if the matrix measure is negative, then we can conclude some kind of contraction. So the next question is how to compute this limit, because first of all, it will depend on the vector norm, because the vector norm defines the corresponding matrix norm. So it will depend, of course, on the matrix norm. And just leaving it in this form doesn't help much. I need somehow to look at A and understand what will be the matrix measure. Now I can prove that the matrix, how can I estimate the matrix measure? So first of all, in the lecture notes that I will send to you, there is a table. Let me write down this table. So in this table, there are 3 vector norms. This is the sum of xi's. This is the sum of xi squared that take a root. This is the maximum of the xi's. These are 3 well-known vector norms for which we have a closed form expression for the vector norm. And for these 3 vector norms, we also have a closed form expression for the induced matrix measure. This is what's written here. So let me see. This is maximum on J, sigma I, Aij. So what is this? You sum up here all the entries in column J of the matrix. You sum up all the entries in column J of the matrix. And then you take the maximum on all these column sums. But every entry you take with an absolute value. Of course, this is not surprising because this is always positive numbers somehow. So this is the maximum on the column sums, where every entry is taken with absolute value. Let me write this one, because this one is very similar. It is the maximum on the row sums. Now it is the maximum on the row sums when every entry is taken as absolute value. And this is a spectral. Here we have a spectral expression. You take A, you multiply it by A transpose, so you get a symmetric matrix. For a symmetric matrix, all the eigenvalues are real, and you take the maximal eigenvalue. Lambda max is the maximal eigenvalue, the greatest of all the real eigenvalues. And then you take a square root, and this is your L2 norm, induced L2 matrix norm. And for these vector norms, matrix norms, we also know the induced matrix measure. So this is very useful because we have explicit expression of these matrix measures, and let me write them. This is maximum on J. So these are exactly the same column sums, but now when I take the column sum, I can keep this without an absolute value. The formula does not require an absolute value for Ajj, and this is very important because if Ajj is negative and it is negative enough, this maximum can give me a negative number. I need this to get me a negative number to get contraction, to reduce contraction. Here it's very similar. It's maximum on I, AIA plus sigma AIJ, I different from J. So this is the maximum on the row sums, but again, the diagonal entry, when I sum up every row, the diagonal entry I don't take with absolute value, I take it as it is, and then we can get negative values. And here, I get 1/2 lambda max of A plus AT. And again, this can be negative. A plus AT is always symmetric matrix. And I look at all the eigenvalues which are all real. I look at the maximal eigenvalue and divide by 2. Of course, this can be negative. For example, just as an example, if A is -1, -2, then A plus A transpose is -2, -4, and lambda max of A plus A2 divided by half be -2. Now I got an error, just a minute. So did I or did I not? Half lambda max of A plus A2, this is -2. Lambda max is -2, sorry. Lambda max is -2, so this is -1. The eigenvalues here are -2 and -4. So lambda max is -2. And this makes sense because you see, what does this matrix do? When you multiply a vector by this matrix, if you look at this system, this means that you shrink at a rate of E minus t in one direction and E minus 2t in the second direction. And in total, you will have a bound on the contraction. This -1 tells you, recall that we had something like E, the integral EUAT, let's do it like this. This told us something about the rate of contraction. So here it will be -t. This makes sense because this is really the bound of the contraction. In the other direction, the contraction is even faster, but we need an upper bound on the contraction. So there are closed form formulas. The lesson here is that there are closed form formulas for this and for this, for the L1 norm, the L2 norm, and the infinity norm. Now, in the lecture notes, I need your advice now. I would like to consult with you. In the lecture notes, I have one example for how to compute this. I have an entire proof on how to compute this, and I'd be happy to give it just so that it will not look so surprising. Where did this come from? Why is it correct? But I don't know how critical this is to you to go over the proof now. It will be in the pages I send you. It will be easier to understand the proof if I do it on the board, I think, but you can also read it in the notes. So I just don't know how much detail you want me to give here. Shall I give the proof of this, or shall I skip it and continue to how to prove contraction using how to prove contraction in the RFM using this? What would you prefer?
You can skip proof if you want.
Skip the proof. Yes? Skip the proof, you said?
Yes, it's no problem. It's up to you. If you want, you can skip. No problem.
Okay, so I skip the proof. Let me just keep the formulas here because they will be useful. Okay. Okay. So now I want to use this matrix measure to prove contraction, proving contraction in nonlinear systems. And then once we do that, we can immediately apply this to the RFM. So how do we take all this construction of matrix measures and how do we use it to prove contraction in nonlinear systems. So remember that we had, this was our nonlinear dynamical system, nonlinear time-varying dynamical system. Now, just for simplicity, let's work with, so that we won't have to write this T all the time. Let's assume that F only depends on X. So this is called a time invariant. A time invariant nonlinear dynamical system. And the key point, remember what is this? This is F1 up to Fn, and each one depends on all the state variables. This is the notation for all the n derivatives. And the key point here is something called the Jacobian. The Jacobian is an n by n matrix where we take df1 to dx1, df1 to dxn, dfn to dx1, dfn dxn. So we take each one of these coordinates of the vector field, each entry of the vector field, and we differentiate each one with respect to every one of the state variables. So this tells me, for example, if I change x1 a little bit, what will be the change in f1? And the change in f1 will give me a change in the expression for x1 dot. And similarly, all the other entries in the Jacobian. This is the key point. Actually, this will play a very important role in our analysis also of contractive systems and also of monotone dynamical systems. This n by n matrix called the Jacobian. Now, we will look at the difference. Remember, when we wanted to prove contraction, we wanted to look at the difference. Now, there was T0 there. Earlier, there was T0 there because we assumed the time varying dynamical system. But now, just for simplicity, let's assume everything is time invariant. I fixed two initial conditions A and B. This is the solution at time t when I started at time 0 at A. This is the solution at time t when I started at time 0 at B. And I want to look at the difference between these two solutions. And in particular, what I want to bound is some vector norm of Z. Now, earlier we saw how to do this for linear systems. But now the problem is that the system is not linear anymore. We have this system. Then there is a trick that allows us to apply the ideas we already saw for linear systems to nonlinear systems. Let me just a minute erase this expression here, just to free up some space, because we need a little space now. Let me copy here the definition of Z. Well, we on time.
Michael,
Yes?
the whole board is visible. You can use the complete board.
I can use the entire board?
Yeah.
Yes, sir, yes.
Okay, somehow earlier I thought like only a portion of it is visible, but okay, excellent, thank you. So, I feel like I have more space now. Let's calculate the derivative of this difference between two solutions at time t. So, by definition, this is this minus this. This is simply from the equation, yes? From the equation, when we calculate the derivative of x, it is just to apply the vector field f on x. And now I make a strange calculation, but you will see that this calculation is very useful. So this is a little bit complicated, but I will explain everything. Oh, I can use the entire board, that's great. What did I write here? I wrote a very complicated way. I used a very complicated way to write the same thing that I had here. So what do? I take R between 0 and 1. So this is, for every R, this is some linear combination of XTA and XTB along a line. Then I differentiate with respect to R, and then I integrate with respect to R. But from the fundamental theorem of calculus, I know that when I take a function, I differentiate it and integrate it, I just get the function in the upper limit minus the function in the lower limit. So the function, the upper limit R equal to 1 is just f xta, which was written here, minus the function when R is equal to the lower limit, which is 0, then this disappears and this is 1 xtb. So this was nothing but writing in a very strange way the difference I had on top. But now, let me be patient with me because this is useful. Now I use differentiation. I have to differentiate f that depends on R. So I know that from the chain rule for differentiation, first of all, I differentiate f with respect to its argument, and then I have to differentiate the argument with respect. First, I differentiate f with respect to its argument, which is just a Jacobian. The Jacobian was, by definition, df to dx. So I put here the Jacobian. And then I have to multiply by the internal derivative with respect to r, which is just xta minus xtb. But xta minus xtb, okay, so this was what I defined as z. This was just z. And also it doesn't depend on dr. So I can put here dr, and I can take zt outside. Nothing changed. And I call all this matrix that now I got something that looks like a linear equation for this. Why is it a linear equation? Because after I integrate this with respect to R, I get some matrix, because J is a matrix. I get some big matrix. And this big matrix, I multiply it by Z. Now imagine, assume that I have such that this is all the time negative for any x in my state space. This will be, after I do this will be some x in my state space. I assume that my state space is convex. I didn't say that, but this will be some x in my state space. Let's assume that this holds. I didn't say that, but it follows from the definition of the matrix measure that it is sub-additive. The matrix measure is always sub-additive. You can prove this by definition of the matrix measure. Well, this thing works for norms, and the matrix measure is simply defined using matrix norms. So you can believe me that this works. Now, from this and this, if these two hold, then the conclusion will be that the integral will also be smaller than minus zeta, because the integral is nothing but a sum of many matrices. If for every x, this is for every x. If for every x this holds, then using sub-additivity that carries over to integrals, I will conclude that this is smaller than minus zeta. I now have a linear system with a matrix here which satisfies this bound. Well, I know already that this would mean this. This we already saw. I call this Coppel's inequality. For linear systems, I know that I have this connection between the matrix norm and the solution. So the idea was I'm looking at a nonlinear system, but when I look at the distance between two solutions, I can use this. This is called the variational equation, by the way, variational equation, because it tells me what happens when I make a variation in the initial condition. How does the solution, the difference between two solutions based on a variation in the initial condition, how does it evolve in time? So, what is the bottom line? All these, okay, and this, what is this? This is exactly what I needed. This means xta minus xtb is smaller or equal to e minus eta, a minus b. By the definition of z, I use now the definition of z, and then I get this. So the conclusion of all these scribbling on the board is that if I have this and I have this for every time t and for any x in the state space, write like this, okay, write like this, then we have contraction. So now I return just to write the theorem. I return to time varying systems. All you have to do, you have to look at your Jacobian and try to find some matrix measure for which this Jacobian is uniformly negative. The matrix measure should be uniformly negative. For any t and x, this should be a negative number. If you have that, then you're in luck, because this vector norm, the vector norm corresponding to the matrix measure, remember we had a vector norm that induced matrix norm that induced a matrix measure. So they are all the time linked. Then when you look at the vector norm corresponding to this matrix measure, you will have contraction. The good news here is that you don't need to know the solutions of the systems, which you never know. You just have to look at your Jacobian, consider its structure, and see if for one of the matrix measures that you know, I gave you three matrix measures, U1, U2, and U3, U infinity, you have contraction. Now, let's apply everything to the RFM. This moment I can erase everything. Well, actually, there was something here I didn't want to erase. Never mind. So, if a matrix measure of the Jacobian is uniformly negative, we can prove contraction with respect to the corresponding vector norm. Now, application to the RFM. For simplicity, I will consider the two-dimensional RFM. You will excuse me. For higher orders, it also works, but we need to play a bit with scaled vector norms. I will talk about this in the next lecture. So this is the RFM. This is our F. This is our F1 and F2. So the first step is to calculate the Jacobian. What was the Jacobian? It was df1 to dx1, df1 to dx2, df2 to dx1, df2 to dx2. So let's make the calculation. I have to differentiate this with respect to x1. I get minus lambda 0, minus lambda 1, 1 minus x2. Now I have to differentiate this f1 with respect to x2. I get lambda 1, x1. Okay, you can continue this. I hope I didn't make any mistakes. df2 to dx1. Lambda 1, 1 minus x2. Minus lambda 2, minus lambda 1. Very good. This is the expression for Jacobian. Of course, everything depends on x. Everything here depends on x. I don't write it. Now remember, we had one matrix measure, U1, which was entries with absolute value, except for the diagonal terms. The diagonal terms we didn't have to take with absolute value. We took them as they are. Now look, here, these terms, the off-diagonal terms, are non-negative anyway. Why? Because our state variables in the RFM are between 0 and 1. x1 is between 0 and 1, the lambda is positive, x2 is between 0 and 1. So here we don't have to take even absolute value of these entries because they are already non-negative. And then I get maximum of these, the sum of these two, which is minus lambda 0, and the sum of these two, which is minus lambda 2, which is always negative, of course. So the conclusion is that the RFM, well, I took the case n equal to, the two-dimensional RFM is contractive with respect to the L1 norm. So I need to look at the L1 norm difference between two solutions of the RFM, one from a point initiating from a point A, and the second from a point B. Everything in our state space, of course. Our state space in this case is a two-dimensional unit cube. And the conclusion is, let's call this minus zeta. It is negative, of course, it depends which one is bigger, but it's minus zeta. E minus zeta t, A minus B. So any two solutions of the system contract to each other by this formula. Questions about matrix measures, matrix norms, and how we used all this to prove contractions in the RFM. No questions? Everybody understands everything, or everybody understands nothing? And in any case, there are no questions. Okay. Okay, so we proved that the RFM is contractive. Also, here I should have written 1. Everything is with respect to the L1 norm. I defined what is the Jacobian. I showed you that proving that some matrix measure of the Jacobian is uniformly negative is enough to prove contraction, and we applied this to the RFM. And now, what are the implications? So let's keep this. What are the implications of contractivity? I already briefly mentioned this in my first introduction talk, but now we can make it more rigorous. So this is proposition 3 on the lecture notes that I will send you. This says the following: if there exists an equilibrium, then xdA minus E in a contractive system, then every solution, this is the solution emanating from A, some initial condition A, evaluated at time t, converges at the exponential rate to the equilibrium. And the proof is very simple. We know that we have contraction, so this follows immediately from contraction. This follows immediately from contraction. I take two initial conditions. One is some arbitrary initial condition A. The second is the equilibrium point, but this is just E. Because if I start at the equilibrium point, by definition, I stay at the equilibrium point. And then this means that this is just E, so I just get this equation. So in the RFM, this would mean that there are some values E1 and E2, and it doesn't matter from what initial condition you start, this will always converge to E1, and this one will always converge to E2. So the initial condition is really, you can think of it as if the initial condition is forgotten. It doesn't matter where you started from in the initial condition. If you wait long enough, you will always approach, you'll be very, very close to the equilibrium, and this happens at an exponential rate. This is also important, the fact that it happens at an exponential rate. So, in some sense, you have a short transient, and after the short transient, you are very close already to the steady state or to the equilibrium. This was the first implication of contraction. Questions about this? Okay, so let me explain another implication of contraction. This is property 4 in the lecture notes that I will send you. Now, we look at the T periodic vector field and assume that the system is contractive. So how can we relate this to the RFM? For example, if now lambda 0 or lambda 1 or all of them change with time, then now we will have a time varying vector field, because the vector field, the right hand side here, doesn't depend only on x anymore. It also depends on time, because for each time you will get a different rate, different transition rates. So we assume contractive, and we also assume T periodicity, which means that this holds for every x and t. If I add capital T, this is called T periodic vector field. Which means that if I add a capital T, maybe the camera turned off by itself, just a minute. Can you still see the camera or not?
Michael, no.
Let's see what happened. The TV turned off. Okay, now it turned on. And what about the camera? The camera. Okay.
You have to zoom. Yes.
Sorry about that.
No problem.
Is it okay now?
Yes,
Can
okay.
you see?
Yeah.
Okay. So we have 5 more minutes. I just wanted to finish. That's exactly good time. I just wanted to finish another application of contractivity. So we have now a time varying system, contractive, and we assume that F is capital T periodic. Then the conclusion is that the system admits a T periodic solution gamma. So gamma is a limit cycle, but it is a T periodic limit cycle, but it is a solution of the system. And from any initial condition, you converge to gamma. So any solution of your system will converge to this unique T-periodic solution, and then you entrain in the sense that the excitation was capital T-periodic, and you converge to a T-periodic solution. And in the RFM, of course, this would mean that if you took here, this is T-periodic with T equal to 1, then when you look at the solutions, you will see that each xi converges to a periodic pattern with the same period, t equal to 1, which is what I showed you in one of the graphs in the in our first lecture. So in the lecture notes, there's a little more about contraction theory. I don't know if you, I don't think you need all that. I also discussed there two other applications of contraction and synchronization when we want to synchronize several agents, and contraction and the design of observers. The design of observers is an important problem in nonlinear systems. I don't know if this is related to your specific work, but anyway, you can look at it there. I will send it to Arvind soon. And I think this is, if I'm not wrong with the timing again, then I think it's time for some questions if you have, and then we can finish for today.
Yes.
And besides question, any feedback is also, you know, control engineers like me know that feedback, especially negative feedback, is very, very important and very, very useful. So don't hesitate to tell me if you want more equations, less equations, if it was too fast, too slow, anything, really.
Sir, am I audible?
Sorry?
Yeah, am I audible, sir?
Hi.
Sir, you talked about synchronization. Here you actually, what do you mean by saying synchronization? Are the like all sides are synchronized?
Synchronization, I mean that you have several agents. So let me speak about the system that I have there. So I have agents, each one follows the same dynamics. Let's assume they are scalar for simplicity. Each one follows the same dynamic, but they start from a different initial condition. And because they start from a different initial condition and follow different dynamics, then in general, they are not equal. Yes, in general, x1t is not equal to x2t. Now, what I want to do, I want to add something called the synchronization term. The synchronization term is what I wrote here. So this gives you all the differences. This adds to x1 all the differences, x2 minus x1 plus x3 minus x1. So this is like the disagreement between all the other agents and x1. And this term should somehow push x1. So the goal is that all the agents converge to some common value C as time goes to infinity. This is what I mean by synchronization. This is a very important problem in multi-agent systems. For example, when you have several quadrotors and you send them out to do some mission together, they have to agree on all kinds of things towards the joint fulfillment of the mission. And this is a classical problem. Let's agree, first of all, on a common value. Let's agree somehow on a common value without a coordinator that tells us the common value is 7. So you try to add to each state variable something that tells you the difference between this state variable And if you design this properly, then you can prove using contraction theory, you can prove using contraction theory that indeed they will all converge to a common value. Okay, so you get here a condition for contraction, which is that for some matrix measure should be negative. This is all in the notes. This is a sufficient condition for contraction, and contraction here would mean that all the agents converge to a common value. So this is the derivative of the scalar function. Maybe you can even write it like this. This is the derivative of S minus ND. What does this mean? As D is increased, you have a higher chance of contraction, because this is like the gain on the disagreement, and it pushes every agent to the right value. And also when N increases, that's also good. It turns out that if there are more agents, there is a higher contraction in general. And also we need this to be not too positive. So this is just an example, another example of how you can prove, how can you use contraction to prove some interesting properties in nonlinear dynamical systems. I didn't have the time to elaborate on this, but I just wanted in the lecture notes to show you that there are many more applications of contraction. Yes, more questions? Well, I know it's late. I know it's late already for you there. It should be 4 and something. So please, 5 even. So I don't want to keep you too late. But if you have any more questions, please don't hesitate. I have time. Here it's early, just 2:30.
Okay. I think we don't have any further questions, so let's close today's session.
Okay.
Thank you all. See you tomorrow as per the schedule.
Yes, very good. Again, any feedback you would like to send me by email, that will help me tune the next lectures to better suit your needs, what interests you or what does not interest you. I don't know. Just send me, please. Don't hesitate. Okay, you're helping me.
Thank you. Thank you.
Thank you, sir.
Thank you very much. See you tomorrow.